Swayam Prabha. Digital India. Educated India.
Hello all, welcome back. In the previous lecture, we were discussing about instantaneous unit hydrograph. We have seen how an instantaneous unit hydrograph can be derived by making use of S hydrograph. So, today we will look into another technique which can be utilized for deriving instantaneous unit hydrograph. We have already seen IUH can be derived using S hydrograph. IUH is the response of a catchment when it is acted upon by a unit impulse input at the time t is equal to 0. So, that response of the catchment is termed as impulse response function, and that is termed as the instantaneous unit hydrograph. So, this can be derived as we have seen the interrelationships between the different response functions. If unit hydrograph is available to us, we can derive the IUH. If S hydrograph is available to us, we can derive the IUH. In addition to that, if you search in literature, you can see there are several methods for the derivation of instantaneous unit hydrographs. So, commonly two techniques are used. First one is Nash model and the second one is Clark model. Here in this lecture, I am going to discuss about Nash model. This is a simple model and this can be utilized for the derivation of instantaneous unit hydrograph. Why do we want to have instantaneous unit hydrograph? In that case, we do not have to bother about the duration. Otherwise, for deriving the unit hydrograph or direct runoff hydrograph, we need to have a specific effective rainfall having a duration d, and corresponding to that we need to have the stream flow records. But always it is not easy to get a uniform rainfall for a duration of d. In such cases, if the duration is not having any importance, that will be better. So, if we are having the instantaneous unit hydrograph with us, we can derive the unit hydrographs and corresponding direct runoff hydrographs from any duration effective rainfall. So, here I am going to discuss about a technique or a model which is known as Nash model, which can be utilized for deriving instantaneous unit hydrograph. So, for that we need to go back to our basics on linear system. We have discussed in detail about Chow and Kulendasamy model. In that we have seen the storage function of a linear system can be expressed as a function of outflow, inflow and derivatives of outflows and inflows. That is, S is the storage. Storage is expressed in terms of outflow, derivatives of outflow, inflow and derivatives of inflow. Depending on the characteristics of the system, this storage function will be having some of the terms presented over here in the storage function. For simplifying the equation, we will be neglecting certain terms based on certain assumptions. In that way, we can assume a concept termed as linear reservoir. For a linear reservoir, the coefficient A1 is taken as K. That is, here we are having S is equal to A1 Q plus A2 dQ by dt. So, and other terms. So, in the storage function we are going to assume A1 is equal to k. All other coefficients are assumed to be 0. So, we can write our storage function S is equal to k q of t. S is the storage function, k storage coefficient and q of t is the outflow. All these parameters, that is I of t, q of t, s, all are functions of time. And here what we are assuming, we are having a storage function which can be considered as proportional to the outflow or output, that is q. So, S is directly proportional to q is the assumption which we are making in the case of linear reservoir. That is why the proportionality coefficient is replaced by a coefficient A1 is equal to k. We can write S is equal to k q t. So, a linear reservoir is the one whose storage is directly proportional to its output. S is equal to k q t, that means k is a coefficient. K is a coefficient, so S can be written as directly proportional to outflow q. So, in case of any problem related to linear reservoir, even if the condition is not given to you, you can assume that the storage is equal to kq. K is the storage coefficient and q is the outflow. Now, we are moving on to Nash model. According to Nash, the catchment is assumed as consisting of a series of n number of linear reservoirs. So, the watershed is represented by a series of n identical linear reservoirs, and outflow from one reservoir is the inflow into the next. That is, if we are considering catchment as such consisting of n number of linear reservoir. So, the reservoir which is at the upstream end or the upper part of the catchment will be producing an outflow, that is the inflow to the next reservoir, and that continues up to nth reservoir. We can schematically represent a catchment as a combination of n identical linear reservoirs like this. Let this be the first reservoir, the water surface is marked over here and it is acted upon by an impulse input. Here in this case, we are going to derive the instantaneous unit hydrograph. What is instantaneous unit hydrograph? The system is acted upon by an impulse input instantaneously at time t is equal to tau, and the response of the catchment is represented by the impulse response function. In hydrology, we will be calling that impulse response function as instantaneous unit hydrograph. So, here in this case, we are going to consider the catchment is consisting of n number of linear reservoirs which are connected in series, and the impulse input is acted upon at the first reservoir. So, the first reservoir is having an impulse input and the outflow from this first reservoir will be the input to the second reservoir. This will be continuing like this, that is Q1 is the input to the second reservoir, Q2 is the input to the third reservoir, and Q3 will be the input to the fourth reservoir. That way we are having n number of linear reservoirs. Why I am specifying linear reservoir? If we are making use of the principle of linear reservoir, we can assume S is equal to KQ. S is proportional to the outflow from the reservoir. So, this Q3 goes to Q4 and finally we are having the nth reservoir. Nth reservoir will be having an input Qn minus 1 which will be producing a response or output as Qn. So, this is the schematic representation of a catchment for which we are assuming the catchment is consisting of series of n linear reservoirs. So, this way we can assume that first reservoir is acted upon by the impulse input, that is continuing like that. Outflow from the first reservoir is the inflow to the second one, that continues up to nth reservoir. Qn minus 1 is the input to the nth reservoir and the outflow from the nth reservoir is Qn. Qn is nothing but the instantaneous unit hydrograph. That is what we are going to derive today. So, we are going to make use of our continuity equation. This is very much familiar to you. Continuity equation is given by IT minus Qt is equal to ds by dt. So, here in this case we know what is the storage function S. Here in this equation IT is the inflow, Qt is the outflow and S is the storage function. We know the storage function S, that is given by Kq, K multiplied by the outflow. So, here we are having the term corresponding to ds by dt. Now, we will go for differentiating the expression for S. So, when we differentiate S is equal to Kqt, we will get ds by dt is equal to K dq by dt. After this, what we will do? We will substitute this ds by dt in our continuity equation. This is the procedure we will be using in any of the rainfall runoff model. Continuity equation is represented by I minus Q is equal to ds by dt. The complexity is coming in the storage function, which is represented by the transfer function. So, this S can be considered as linear, non-linear, depending upon the knowledge about the system. We can derive the mathematical expression related to that particular system. Here we are considering the storage function S is directly proportional to Q, considering the system as a linear reservoir. So, the same procedure can be utilized in any of the rainfall runoff models for carrying out the hydrologic analysis. So, ds by dt we have found the expression, this we will be substituting in the continuity equation. So, our continuity equation becomes IT minus Qt is equal to Q dq by dt. What is our aim? Our aim is to determine Q, that is certain input is there, that is acting on the catchment, some output will be there. For example, some amount of rainfall is occurring on the catchment. After considering all the hydrologic processes or some of the hydrologic processes which will be taking place within the catchment, finally we will be getting the runoff at the outlet. That runoff computation which we are intending for, which is representing by Q. So, we need to compute the value corresponding to Q. What we will do, similar terms, that is here we are having Qt, here we are having dQt by dt. Similar terms will be taken towards one side. So, we can write I of t is equal to Q of t plus K dQt by dt. We will do some rearrangements with the terms. dQt by dt plus 1 by k Qt is equal to 1 by k IT. Now, we need to find out the solution of this differential equation. This is a first order linear differential equation. We have considered our continuity equation. In that, we have substituted the expression for ds by dt, time rate of change of storage is written in terms of derivative of the storage function. After that, we have rearranged the continuity equation for finding out the solution, that is for finding out the outflow from the linear reservoir represented by Q of t. So, the equation is now in the form of first order linear differential equation. You must be already knowing how to find out the solution for an ordinary linear differential equation. You will be already knowing different techniques for finding out the solution of an ODE. So, what we will be doing? We will be multiplying both the sides of the equation by integrating factor e to the power of t by k. Then the equation takes the form like this. Just we have multiplied both the sides with e to the power of t by k for getting the solution easily. You can look at the left hand side. Left hand side is given by e raised to t by k dq by dt plus 1 by k e raised to t by k qt. So, the left hand side can be written as d by dt of qt e raised to t by k. You apply product rule for this expression and you will get this left hand side. So, d by dt of qt e raised to t by k is equal to it by k e raised to t by k. Now, for finding out the solution, we will integrate this equation. When integrating, we need to substitute the limits. So, for that we are going to make use of the initial conditions. Q naught equal to Q0, Q at time t is equal to 0 is equal to Q naught. So, we can integrate the above equation. Before integrating, we are going to introduce a dummy variable of time. Only for time variable, we are substituting a dummy variable tau in the integration equation. So, it can be rewritten as this equation can be modified like this: integral q naught to qt d qt e raised to t by k is equal to 1 by k integral 0 to t e raised to tau by k I tau d tau. We have replaced t by tau. This is just a dummy variable of integration. So, the same equation is repeated here and we are going to integrate it. You consider the left hand side, integral q naught to qt d qt e raised to t by k. So, when we integrate that, it will be taking the form of qt e raised to t by k. The limits are varying from q naught to qt. At time t is equal to 0, q is q naught, and at time t is equal to t, it is represented by qt. So, that is what is written over here. So, the left hand side after integration, it will be taking the form as shown here. When we substitute these limits in this qt e raised to t by k, so upper limit if we substitute, it will be qt e raised to t by k minus q naught e raised to t is 0, e raised to 0. So, that will be taking the form q naught. So, the left hand side will be taking the form qt e raised to t by k minus q naught, that is equal to 1 by k integral 0 to t e raised to tau by k I tau d tau. Now, what we will do, our intention is to find out qt. We will take q naught to the right hand side and also e raised to t by k to the right hand side. So, qt will be taking the form q naught e raised to minus t by k plus 1 by k e raised to minus t by k integral 0 to t e to the power of tau by k I tau d tau. Here you can see we were having e raised to t by k on the left hand side. First what we are doing, we are taking q naught to the right hand side. So, q naught plus this term has come and then we are taking e raised to t by k to the right hand side. Then it will be taking the form e raised to minus t by k. So, that way we have written the expression for q of t. So, this equation can be modified again as q naught e raised to minus t by k plus 1 by k integral 0 to t e to the power of minus t minus tau by k I tau d tau. These two terms, e to the power of minus t by k, e to the power of tau by k. So, these two combine together to form a single term and we got the expression like this. Now, at time t is equal to 0, q naught is 0. For a system which is starting from rest, initially q naught is 0. After that, some impulse is acted upon that and the response is coming. So, at time t is equal to 0, we can put q naught equal to 0. That is the case with a system which is starting from rest. But in some other case, it may not be at rest initially. In that case, what is the value corresponding to q naught, that has to be substituted. Here we are considering q naught equal to 0 at t is equal to 0. So, our qt will be taking the form 1 by k integral 0 to t e raised to minus t minus tau by k I tau d tau. This is the expression for qt. So, here we are considering an impulse input. For an impulse input, IT is equal to 0 when T is not equal to 0. What is the characteristics of unit impulse input? An impulse input which is having a value of unity is acted on the system at time t is equal to 0 instantaneously. At all other times it will be equal to 0. That is what is written over here. IT is equal to 0 when t is not equal to 0. IT is not equal to 0 when t is equal to 0. Now let us look into our equation for Qt which we have derived. Qt is equal to integral 0 to t 1 by k e raised to minus t minus tau by k I tau d tau. What we are going to do, we are having the convolution integral which is the response of a system from a continuous pulses of impulse inputs. So we will compare the output q of t with the convolution integral. So you can find out that ut minus tau is equal to 1 by k e raised to minus t minus tau. Compare these two equations. We are having I tau d tau, here also I tau d tau is there, and here the extra term coming is ut minus tau, that is nothing but our impulse response function. Here instead of ut minus tau, we are having the value corresponding to 1 by k e raised to minus t minus tau by k. So we can write ut minus tau is equal to 1 by k e raised to minus t minus tau by k. What is ut minus tau? Ut minus tau is the impulse response function. A system is acted upon by an impulse input at time tau. The response from the system after a time tau, that is at t minus tau, is given by ut minus tau. That is nothing but our impulse response function represented by the output from the first reservoir. So this is the output from the first reservoir. According to Nash model, this output is the input to the second reservoir. So this expression can be simplified in this form. UL is equal to 1 by k e to the power of minus L by k. So this is the outflow from the first reservoir. So that can be taken as the inflow to the second reservoir. That is what we are going to do. This is our output expression, and we can write for the first reservoir the impulse input is applied at time t is equal to 0, and the corresponding output will be the input to the second reservoir. So in terms of tau itself, we are writing q1 is equal to, that is we are not making use of the terminology u here. Output from the first reservoir is written as q1. q1 is equal to 1 by k e to the power of minus tau by k. As the variable of time, instead of L, we are substituting tau itself. Any variable can be substituted over here, but we were comfortable with the usage of tau, that is why I put q1 is equal to 1 by k e raised to minus tau by k. This is our input to the second reservoir, that is IT for the second reservoir is 1 by k e raised to minus tau by k. Now what we will do, we will substitute for I tau in the case of second reservoir. So Qt is equal to 0 to t 1 by k e raised to minus t minus tau by k 1 by k e raised to minus tau by k d tau. So this can be simplified as integral 0 to t 1 by k square e raised to minus t by k d tau. 1 by k square e raised to minus t by k d tau. So we can write with the notation 2, that is the output from the second reservoir q2t will be t by k square e to the power of minus t by k. So this expression, when you integrate, you will get this expression. Now this is the outflow from the second reservoir, that is the inflow to the third one. So this is the inflow to the third reservoir. So the output from the third reservoir can be written as q3t is equal to t square divided by 2k cube e to the power of minus t by k. Step by step when you do the integration, you can get this expression. When it goes to the fourth reservoir, this term will be 3 and this will be 3 and k to the power of 4 will be coming. So, using the same procedure, we will go up to nth reservoir. We can write Qnt as t to the power of n minus 1 divided by n minus 1 factorial k to the power of n e to the power of minus t by k. So, compare these two equations for understanding more. Q3t, this is the output from the third reservoir. Here we are talking about the output from the nth reservoir, that is Qnt, and t to the power of 2, that is for the third reservoir it is 2. Here definitely it will be t to the power of n minus 1, and here 2 in the denominator we are having 2, next term it will be 2 into 3, 2 into 3 into 4, that way it goes on up to n minus 1 when we reaches the nth reservoir. So, this will be n minus 1 factorial k to the power of n, k to the power of 3 will be replaced by k to the power of n e to the power of minus t by k. So, this is the output from the nth reservoir. So, this is nothing but the instantaneous unit hydrograph from a catchment with parameters k and n. We are having two parameters n and k. K is representing the storage coefficient or reservoir coefficient, and n is the number of reservoirs which we are considering. So, these two values will be varying depending on the characteristics of the catchment. The parameters can be determined from the rainfall and flow data. K and T are in hours and Q is in centimeters per hour, because we were discussing about 1 centimeter rainfall instantaneously acted, right, in the case of an impulse input. So, this expression is giving us Q in the unit of centimeters per hour. So, if you want to get the Q in meter cube per second, you need to make suitable conversions. So, the outflow from the nth reservoir we have computed, and that is the response of the system. So, initially how we have considered? We have considered the catchment consisting of n number of series of reservoirs. Outflow from first one is the inflow to the second one. That way we have proceeded and we have made use of the continuity equation and the concept of linear reservoir S is equal to KQ for deriving this equation. So, for the derivation of IUH, we can make use of this formula Qn, and that IUH can be utilized for deriving the unit hydrograph and the corresponding direct runoff hydrographs from different effective rainfalls. So, here there is two things to be known, that is determination of n and k. These parameters n and k. So, these parameters n and k can be determined by making use of the effective rainfall hydrograph and the direct runoff hydrograph. So, that I am not discussing in this lecture. For that we need to make use of some probabilistic concepts. So, as of now, how the IUH can be derived and what is the IUH ordinate Q, that is represented by Qn, that we have found out by making use of this expression. Given n and k, you can determine the instantaneous unit hydrograph for a particular catchment. So, now what we are going to do, we are going to write the generalized expression for Nash IUH. So, this is the expression which we have derived in the previous slide. So, that we are going to make in a generalized form. So, Q and T can be written as Q and T is equal to 1 by k gamma n T by k to the power of n minus 1 e to the power of minus t by k. E to the power of minus t by k is here, t to the power of n minus 1 is there, divided by k to the power of n is there. So, what we have done, k is written in terms of k multiplied by k to the power of n minus 1 and t and k combined together. That way we have written t by k to the power of n minus 1. Then comes the term that remaining k we have separately kept, and n minus 1 factorial is written as gamma n. For writing the expression in a generalized form, we have made certain modification with the terms, and we got the expression like this. Here gamma n is the gamma function. If n is an integer, gamma n can be written as n minus 1 factorial, that is the one which we have derived, and it can happen in such a way that n can be a fraction also. So, it has to be calculated using gamma function. Gamma function provides one table corresponding to different values of n, you can get the value of the gamma function. So, here in the case of gamma n, if n is an integer, we can calculate it directly without making use of the gamma function table, that is by using n minus 1 factorial. But sometimes it can happen in such a way that n can be a fraction. In such cases, we have to make use of the gamma function to get the value corresponding to that. Here what we have assumed, the catchment is considered as consisting of n number of linear reservoirs connected in series. So, this n becoming a fraction, in the actual condition it is not possible. If we are explaining theoretically, we can consider n as a fraction. So, that way if we are considering n as a fraction, then we have to go for making use of gamma function, and from that we have to find out the value corresponding to gamma n. Gamma function in every textbook, the table is given, corresponding to that we just have to take the value, it is not a difficult task. If it is not a fraction, that is n is an integer, we can calculate gamma n by making use of the n minus 1 factorial. So, that way we can compute the ordinates of the IUH for different t values. The references are given. For having more understanding about the topic, please refer these textbooks. Here I am winding up this lecture. Thank you.